Okay, look, we're starting to look at this whole electromagnetic induction area, which you mean nothing to you at this stage. So let's just have a quick review of magnetism as we know it. In year 11, we had this whole idea that a wire with electrons flowing in it, so it has a current flowing in it, had a field that sort of went around the wire in a circular direction. And we used our right-hand rule to determine the direction. If the current, we used the right thumb in the direction of the current and our fingers wrapped in the direction of the magnetic field. So we had this whole idea that magnetic fields around a wire went in a circular direction. This, at the time it was discovered, seemed pretty silly, and you know, what could you do with it? But we then went on to find that if we wrap the wire in a solenoid and put our voltage through it, that all the little magnetic fields were able to line up, and so we would then end up getting a similar field to what we got in a bar magnet, which was interesting because what we were basically doing was electrically making a bar magnet. This became the north, this became the south. We looked at field lines. Field lines were important. So we're able to get these circular fields around a wire to line up in a solenoid and create a uniform field through that solenoid. We had a few equations. The magnetic field away from a wire was equal to B, and we had this whole mu naught, which is magnetic susceptibility. We said that if the current was bigger, the magnetic field was bigger, but that the distance was inversely proportional with distance, which means as the distance gets bigger, the field gets smaller. The mu naught over 2 pi, sometimes because mu naught was equal to 4 pi times 10 to the minus 7, sometimes we would divide that whole thing by 2 pi and call it k, which was 2 times 10 to the minus 7. So that was our strength of a magnetic field near a wire. There is also a formula for the magnetic field in a solenoid, which is just, again, mu naught n, number of turns per meter, times I, the current through it. And that gives you a uniform field inside the solenoid. So you can make a uniform field inside a solenoid just like you can make a uniform electrical field with a capacitor. The capacitors we talked about as storing charge, didn't we? The magnetic field doesn't really store charge, but it creates there is energy in the magnetic field just as there is in the electrical field. We found some interesting things with these ideas. We found that if you had a coil, and this was a coil that didn't actually have any current flowing through it, if we pushed a north there, then it would set up a field to oppose that, and we called this Lenz's law. Some of you, we're getting onto the stuff now that you may not be so solid with. So we were able to determine the direction that the current would flow. So the current would actually flow in here if you pushed a north in, and when you pulled it out, it would flow back the other way. And we called it Lenz's law because what basically was happening was it was always going to create a field to oppose the field that was changing. So when you have a north, remember a north, if we have a north, the field goes out, then it curls back around, right? So when you stick a north into a solenoid, the field that you're making is a field going inside the solenoid. So the solenoid's going to make its own field going out. And so basically what it's going to make is a north. So when you push the north in, it makes a north. But when you pull the north out, suddenly the field, we've got a field like that that's decreasing in size. So it's going to then try and make one that's going to increase in size. And so it's actually going to make a south when you pull it out. So it always opposes the change. The change not being the direction, but the strength. So if you've got a field going that way and it's increasing, then it makes a field that way. If you've got one going that way that's decreasing, then it makes one that way. So it always tries to oppose the change. And this we called Lenz's law. And we're going to see more of Lenz's law. The big thing from, I think, level 2 was the Lorentz force law. I'm just trying to get my video back. Stupid computers, the school makes them turn off every 5 minutes, which is really annoying. So the Lorentz force law was to do with the force on moving charges. So if we look at a moving charge, we could call it an electron, for example, and it's just moving. It's got to have a velocity. This all is determined by velocity. So you need a magnetic field. And remember how we drew our magnetic fields? This magnetic field means a magnetic field going into the page. Everything you're going to do, you work with the right hand. So a field going into the page, you use your fingers and you point them in. That's the direction of the field. If they were dots coming out, like that, that's the field coming out, then your fingers point out with your right hand. Okay, so in for a field going in. Then, if you're going to use this Lorentz force law, which mathematically was a law that basically said that the force on a moving charge was equal to BQV, V being velocity. And this is a moving charge. Field, velocity, and the palm gives you the force for a positive charge. So the back of your hand gives you the force for a negative charge. So this electron, when it's in this field, will feel the force down, and it will go in a circle. I've done another little video that will help you determine the radius of that circle. But this one is so important for working out nearly everything. B is the magnetic field strength, Q is the charge moving through the field, and V is the velocity. Now remember, the charge must be moving perpendicular to the field, or have a component that's perpendicular to the field. So it can be moving at some strange angle, and you didn't work out the component that's perpendicular to the field, which is going in, and that would be your force. So this is normally a vector equation, but we don't do it as a vector equation. So if the electron was moving with the field, that's into the page or out of the page, it's got no component perpendicular, it would feel no force. So those are the important things to do with the Lorentz force law. Alright, I think we'll leave it there.